Hi everyone, let's talk about homework 5. In this homework, I'm going to focus on which tool we are supposed to use for a given scenario. For instance, if you have one sample and your data is normally distributed, probably you should be thinking of one sample t-test. But if you have two samples and one of them being non-normal and you don't have large enough sample size, then you should probably consider permutation test or Mann-Whitney-Wilcoxon test. And there is a table in your textbook, I believe it's 3.1.1, and that you can look up. It is a big roadmap and you can look up any tool you're supposed to use for a given scenario. It is very, very detailed. By the way, you are supposed to be able to implement most of the procedures that we talked about in R, and that will be reflected not only in the homework but also in the final exam. So without further ado, let's get started. Before we move on, I'd like to recommend you guys to double check all the data that you have typed in because in this case we do have a large amount of data. So a quickest way that you can do this is to calculate the mean and standard deviation for each of the group. If the mean and standard deviation of these two groups match up with what's in the textbook, probably you're fine. But if it doesn't match up, then you should double check your data and make sure everything is right. So as you can see here, the mean of the first group is 2.58, matches with what's in the textbook, and standard deviation is 0.65, also matches with the first group, and the fertilized group also looks all right. So let's move on. So in order to do the two-sample t-test, the command is t.test, and you have to pass in these two groups. But there are several questions that we should ask ourselves when we are doing t-test. And one question is, okay, is this pair t-test or independent two-sample t-test? And obviously it is independent two-sample t-test because there is nothing like before and after. There is no such description whatsoever. This is not paired t-test. We can specify this option as false. And the next question we are supposed to ask ourselves is whether or not this is a two-sided t-test. And obviously it is, because the background information, it says we want to test whether the fertilizer has effect on average radish growth, which means there is no specific direction in mind, so we can use something non-directional. That means the alternative is two-sided. Well, that is everything, and let's run the code. Here we got the p-value, which is 0.004696, which is smaller than any alpha threshold that we can think of. So obviously we are going to reject the null hypothesis and claim that there is significant difference statistically between these two groups. And two more things before I move on. As you can see here, I specified the paired equal to false and alternative equal to two-sided. But if you have been in my lecture, you would know that by default, the t-test assumes pair to be false, so which means we don't have to specify it. Computer will think you are doing independent two-sample t-test automatically, so you can actually take this off. And similarly, the computer is going to think you are doing two-sided t-test automatically unless you are specifying otherwise. So actually you don't have to specify this. So this is the minimal amount of code you have to type in. You can just run this code again and compare these two chunks of output. They are identical. Another thing that I want to point out is in the homework, I strongly recommend you guys to not only just copy and paste the output, this part, into your homework, but also explain things into that 5-step hypothesis test format. By which I mean, in step 1, you are supposed to state the null hypothesis and alternative hypothesis. In step 2, you are supposed to present the t-statistic. In step 3, you are supposed to present the p-value and compare it. And in step 4, you are supposed to kind of give a conclusion based on the comparison of p-value and the alpha value. And in step 5, you should be able to explain your findings in the context of this problem, which means, in this experiment of radish growth, the fertilizer group and control group, there is a statistically significant difference. Okay, this question is about type 1 error and type 2 error. Before we move on and talk about the question, I'd like to take a minute to review the definition of these two things. So type 1 error actually means, given the fact that there is no difference between these two groups, in other words, H0 is true, but we forcefully rejected the null hypothesis and claim that there is significant difference. On the other hand, the type 2 error means although the alternative is true, but we somehow stick with the null hypothesis. And in this specific question, if you read about this context, it says the FDA approves the drug. That means FDA rejects the null hypothesis, which is the drug is not effective. So in other words, there is significant evidence for HA. So if they approve the drug, the only possible error that they can make is type 1 error. The 7.3.5 it's still about type 1 and type 2 error, but the question is what type of error would you commit if the null hypothesis is not rejected? So obviously, if you don't reject null hypothesis, your decision is in this category. So the only possible error that you might commit is type 2 error. So remember, this is different from the previous case because as the FDA case says, if you reject the null hypothesis, the only error that you are going to commit is type 1 error. For this question, the short answer is yes, we are supposed to reject the null hypothesis. The long answer is yes, we can still conduct the test using confidence interval because a 95 confidence interval can be used to perform a 5% level of significance test, and that is called duality principle. And specifically, if that confidence interval you generate is positive, in other words, the confidence interval of mu1 minus mu2 is positive, then we are supposed to reject the hypothesis that mu1 minus mu2 equal to 0 because that confidence interval does not include 0. And in contrast, if the confidence interval does include 0, then we cannot reject the null hypothesis that mu1 minus mu2 equal to 0. Well, this is a really tricky one because first of all, you have to understand how duality principle works. Duality principle only works when the confidence level and alpha are complement. If it's a 95 confidence interval, it will only work for alpha equal to 5%. But if you read closely about this question, it says 95 confidence interval and alpha equal to 0.1. So in this case, you cannot use duality principle directly. Actually, you can still use duality principle in some shape or form, but not just directly. See if you can follow my logic. Based on the duality principle, you can say because this 95 confidence interval is totally negative, it does not include 0, we have to reject the null hypothesis at 5% level, alpha equal to 0.05. That is exactly how duality principle works, but that's not what we want because we want alpha equal to 0.10. But this is what we can say. Because we have rejected the null hypothesis under 5% level or under the scenario in which alpha equal to 0.05, this p-value, whatever this is, has to be smaller than 0.05. And because it is already smaller than 0.05, then it has to be smaller than the alpha level that we are talking about, which is 0.1. So whatever this p-value is, it has to be smaller than 0.1, and we have to reject the null hypothesis. This is a complete argument to reject the null hypothesis based on duality principle. Again, it is not a direct application of duality principle, but we can have some workaround to answer this question. I also assigned 7.5.6 as a homework problem. I only assigned the first two parts, part A and part B. I want to compare the difference between directional and non-directional in the R code implementation. So first of all, you have to, scan in all the data and make sure you have typed in the data correctly. So part A is a non-directional t-test in which you don't have to specify anything in terms of alternative because R is going to use two-sided as a default alternative, and we are going to have a p-value which is 0.015, which is smaller than 0.05, and we are supposed to reject the null hypothesis. And again, I recommend you to write everything down in terms of the 5-step hypothesis procedure. Part B has a direction in which we want to test if the mean of experimental group is greater than the mean of control group. In that case, we have to specify the alternative. We have to pass in order correctly. So we want to test experimental is greater than control. So we have to pass in the order as experimental, control, and alternative equal to great. And if we run this line of code, we are going to end up with a slightly different p-value, which is 0.007727. That p-value is still smaller than 0.05, and that's why we can still reject the null hypothesis. Okay, 7.5.13. You have a lot of data here, and I'm going to upload the data in the course document in which you can find all the slides. I'm going to upload a file of all the data from question 7.5.13, so you guys don't have to type it in yourself. Question here is pretty simple. You are just supposed to do a 2-sample t-test, and these are independent samples. This is a code you are supposed to run. You got a p-value that is 0.049, and that is smaller than 0.110. So you are supposed to reject the null hypothesis and claim there is a difference among these two groups, and that is it. I also want to point out that although I changed this confidence level, but I actually don't have to. So I want to compare what is going to happen if I remove this conf level equal to 0.90. Obviously, the confidence interval is different. If we specify conf level equal to 0.9, we will get a 90% confidence interval. But if we don't do anything, we are going to get a 95 confidence interval. However, we are only concerned with p-value here, and that doesn't change. The p-value in the first case in which we specified the conf level is 0.049, and after we removed that argument and we end up with the same p-value. And the only thing that matters here is the p-value, because we want to compare that with our alpha level. What I'm saying here is if you only want to do a hypothesis test, you don't even have to change the specification in terms of confidence level. That argument, conf level, is only relevant if you want to generate a confidence interval. You don't have to do anything if you just want to do a hypothesis test. In 7.7.1, we are supposed to do a sample size determination. In other words, we have desired power in our mind, and we have determined how many observations are we going to collect in order to achieve that power, because the more data we have, the more powerful the test will be. There is like a minimal amount for us to achieve a certain power. So you can obviously calculate everything by hand, but I recommend you to use this R function, which is power.t.test. And in this function, you are supposed to specify all the parameters like delta, standard deviation, and significance level, and power, and a lot more if necessary. So in this case, I have already figured out from the background information that standard deviation is 0.3 and significance level, which is type 1 error, is 0.05. But if you look into these two scenarios, John and Smith, they are saying something different. So in John's scenario, the true difference that he is talking about is a quarter. He is saying something like reasonably sure, which is quantified as 80%. In his scenario, what we are supposed to specify is delta equal to 1/4 and power equal to 0.80. And in the next scenario, which is about Smith, the statement is about 1/2 or half centimeter. And the statement about power is very sure, which is later quantified as 95%. Copy and paste this line, but change the delta into 1/2 and power equal to 0.95. So you have to be very careful, because in the first case and the second case, two parameters has been changed, both delta and power, and they lead to very different results. So I'm going to explain to you first the concept of meta-analysis. We talked about this in class before. In order to understand the 95 confidence interval, you have to try to think of, calculate the confidence interval over and over again with different sample, which means, if you look at the distribution, you take a sample, and for that sample you have a confidence interval, and you keep sampling, and so you get another sample and you have another confidence interval, and then you have a lot of confidence interval. And under that circumstance, if your procedure is right, then 95 of all these intervals that you have just calculated would cover the true value. But in real life, we only have one chance, and it's like hit or miss. So if the mu is in your confidence interval, then it's in your confidence interval. If it's not, it's not. There is no randomness anymore because you only have one sample. The same notion also applies to hypothesis test. If you really think about any hypothesis test, it either ends up with yes, we have to accept the null hypothesis, or no, we have to reject the null hypothesis. That is it. There is no probability statement. So for each of the one hypothesis test, you can never say something like there is a 4% chance that H0 is true. What you can actually say about that 4% is actually there is a 4% probability that you are going to see something that is even more extreme or crazier than the value you have observed. That is what that 4% means. And that happens to be part D, which is the right interpretation of a p-value. Part B is obviously right because the p-value is smaller than 0.05 and we are supposed to reject the null hypothesis and embrace the alternative. And part C is a little confusing because it looks like a meta-study statement, but it is not. Because first and foremost, if you read the statement, it says, if we repeat the experiment, there is a 4% chance that we would reject H0 again. This is that wrong because we don't even know if H0 is right or wrong. How would we know the likelihood of rejecting it if we repeat this experiment? A right way to say this under the meta-study, it should be something like, if H0 is right, then there should be a 5% chance that we still reject H0. Remember, that is actually the definition of the type 1 error, because type 1 error is a probability that even though H0 is right, we still have some probability, which is alpha, to reject the null hypothesis. No matter what angle you are looking at part C, it is a wrong statement. The last question, 8.2.1. In the first step, you want to calculate the standard error of the mean difference between two varieties. So this is how you are supposed to do it. Pass in the first group and second group. So as you can see here, in order to calculate standard error, we have to first calculate standard deviation and then divide it by the square root of the sample size. The difference is G1 minus G2, so we calculate standard deviation of that and divide it by the square root n. So that is 0.337. So in part B, you want to pay attention to the fact that this is a paired t-test, and the way to do it in R is to specify paired equal to true, and the p-value is 0.016. And if you compare this with 0.05, obviously you should reject the null hypothesis. But in terms of part C, interestingly, it asks you to do something not right specifically. You are supposed to treat these two samples as independent sample tests, and this is how to do it. Remember, if you don't specify the pair equal to true, R is going to treat group 1 and group 2 as independent samples automatically. As you can see here, we get very different p-value. In this case, p-value is 0.2277, and we cannot reject the null hypothesis. Because of the choice of which test you are going to, it will have a major influence on what kind of conclusion you can draw from the procedure. If you compare the confidence interval that has been generated by both cases, in the pair t-test is from negative 2.7 something to negative 0.57, but when it comes to the two independent sample assumption, we will get something from negative 4.6 to positive 1.355 something. So this confidence interval is much wider than this one. And even without jumping into mathematical details, we can actually make sense of it because we are removing the variability among individuals. We are going to expect much less variability compared to two independent samples, and that explains why we are having a much narrower confidence interval if we are employing a paired t-test.